Hi everyone, welcome back to another video, and in this video I'm going to be showing you all how to make a 2D platformer with Bevy and Rust. The end result of this video is basically going to be a playable character controller that has Tilemap Collisions. First off, the tiled editor is going to be what we're using for our tile maps. So this is what it looks like in the editor. We've got a collision layer, which is pretty self-explanatory, and we've also got an object layer, is what they're called in tiled. So you can move around different objects, customize their properties. We're not going to be going into the properties in this video, but we are going to be creating a player object layer, which lets us drop our player anywhere in the scene we want. So if I move it over here and run the code again, our player should be over there instead. To download the tiled editor, just go to their website, mapeditor.org, and download it on itch.io. I'd also like to add that the source code for this video, it's all on GitHub, and I will be linking this in the description right after I finish taping this video. So let's get started. First thing I want to do is show you guys how to create your own tiled map, because not everyone is going to be using the same assets folder. Actually, I would appreciate it if on your first walkthrough of the tutorial, you download the assets folder that I have linked in the GitHub description, because if you use my assets, then nothing will go wrong in the video. So if you want to make your own assets, then maybe use my assets first and then change them after you've followed the entire tutorial. Okay, so let's go over how to create a tiled map. I'm gonna delete the current one I have right now. And then inside of tiled, it's gonna say that that file's gone. So let's just make a new map. The width and height of each tile, you can determine this based on your tile set. So my tile set has a 16 by 16 tile size, so I'll just leave it be. Make sure you don't check the infinite checkbox here, because we're not going to be supporting infinite tiles in our loading function. Anyways, let's create a new tile set. Checkmark embed in map, and then just browse to where your tile set is. Okay, now let me just create a basic floor. Call this player collision, and if I create, I'm gonna use the rectangle tool to more easily create the floor. Also, you can flip the tiles. So right now this doesn't look very good, but if I click X, I can flip it. You can also flip it on the Y, so if I want to recreate like a ceiling like I had before, I can flip it on the Y, flip this on the Y, and we've got a simple tile map. Now let's press Ctrl S to save our map as map.tmx. Okay, now let's get into the actual code of this game. I'm gonna delete everything I have for now, so that we can rewrite it. Before we rewrite our code though, go to your cargo.toml file, and we're gonna change a few dependencies here. Obviously we have Bevy 0.16. You don't need to have the dynamic linking features, but and this library here, it just makes compilations faster. Whenever you build the project, you actually have to just delete these, and if you want to release the project, you're going to delete these so that you can build it normally. Now we also have the Bevy ECS tilemap library, which is going to help us. It's a library that helps us render our tile maps. And then all of these libraries, you should just copy them into your file, into your cargo.toml file, because these are going to help us load in our actual tiled map. Okay, now let's get started. I'm just gonna create a simple window for now, just to test out if our Bevy is working. I know it's working, but it might not work for you, so it's best to get that out of the way before you start coding the actual game. And if I run cargo run, we should have a window. Okay. Now, first thing I'd like to do is create a new folder called game, a file called game.rs, and a module file. I like to do this to organize my project so that not everything, let me turn this sound down, hold up. So that not everything is stuck in our main file. It makes it a lot more organized. So let me just create a new plugin called the game plugin. And then we can include the game file inside of our main function and also add in the game plugin. Now we basically don't really need to touch this file at all anymore, this main file, because we can basically do everything inside of here. A plugin I'd like to add is the Tilemap plugin, which is going to help us render our tile maps later on in the game, or later on in the tutorial. And then let's create a folder called tiled. This is going to help us load in our tiled map. And then include the folder, this module file. Start by importing Bevy plugins and creating a tiled plugin. Okay. So what we have to do first is create an asset. Type path asset. Okay. And then this asset is basically, we're going to be loading in all our data to this asset. So this asset consists of a map, which is our tile. We're going to have to import this. What? Oh, okay. I guess you don't have to import it. Then we also have to have a hash map of tilemap textures. Before let's import this first. Import the std collections hash map and import the tilemap texture. Before I continue though, I basically remodeled the Bevy ECS tilemap example for tiled in this video, and the reason I did that is because some of the code, for example this part, that's not really what we want in a game. This is more so to like demonstrate the functionality of the Bevy ECS tilemap plugin, but this is not really optimized for an actual game. So I decided to rewrite a lot of it, and that's why I'm going over this instead of telling you to just copy and paste that part into your code. Anyways, to actually load in our tiled map, just first register our asset actually. App.register. Oh no. I think it was init asset. Tiled map. Okay. We're gonna have to write a lot of boilerplate code to actually load in the map. And to start off, we have to define a bytes resource reader. And this is gonna help us load in our file later on when we write in the load function. Gonna have to import this. And then create a constructor for this, which is basically just us passing in some bytes. You don't really need to understand some of the boilerplate Most of it is just there to help us load in the actual data from the file. But of course, we have to write some of our own code to spawn in the map from the data, and that's the part you should really be able to understand. That's because you're gonna have to modify that part if you want to add in functionality to your game. Like this stuff here, you don't really need to know what it does. It's just there to help it load. Okay, so let's implement the actual resource reader trait for our byte resource reader. And then the type of resource is this. Obviously, we have to import this. Should be the stdio cursor. And then error type, let's just set it to stdio error. And then it autofills for you this function. And then we just have to return the bytes. Okay. Now let's create the actual load function. So first, let's define an error type. We have to do this again for boilerplate purposes. Could not load tiled file, and then it's gonna say what the error was. It's not a structure, it's an enum. Then we're gonna have to derive some traits. The error type is, there's a lot of things named error, but what we're gonna be using is this error type. We're not gonna be using this. Let's just get rid of that warning. Now define a tiled loader. And we're gonna implement asset loader for this tiled loader. The type of asset, it's gonna be our tiled map, obviously. We're not gonna define any settings, so let's just leave that as a blank tuple. And the error type is what we just created, so let's just pop that in. And now let's create the load function. Is it just auto create it? Oh no, okay. Let's create the load function. I think it should auto create if I import this. Hold up. Yeah, okay. So import the asset loader with quick fixes first, and then it should auto create most of it. We're not gonna need this part, so just delete that part. And then let's create a vector to store our bytes, and then read in the bytes from our file. Next, let's create a loader. This is again a lot of boilerplate that you don't actually need to understand most of it. It's only some select parts which are helpful to know. I'll point those out later. There's actually, I made a typo here. There's only one of these. And then let me just get this down here. It should be easier to see if I zoom in. Let me just zoom in. we're gonna load in our TMX map. And then if we fail to load our map, we can write an error message. Could not load TMX map, and then write the error type, what the error was. Gonna have to import error kind. Alright, now this part is actually kind of important. You should understand this part. We're gonna load in the textures for our tile map. So let's iterate over all the tile sets in our tile map. In map.tilesets, iterate dot enumerate. I don't know why. I think the error message will just go away later. So let's match our tile map texture. Oh wait, this is an async function. And we've got to create a lifetime for this too. If there's no image, we're just gonna say we're gonna continue, and we're gonna log an error message. Unsupported tile set type, let's say that. Tileset.name. Right now it's the Rust analyzer can't inference the type, but later on it's gonna inference the type. So just bear with me. And then the texture path should be the source of the image. All we have to do is load this now. Load context.load texture path, and then insert the texture into our, or actually we don't need to insert it yet. Just store it as tilemap texture. And now, after we get the tilemap texture, we can insert it into the hash map. Yeah, we gotta change it. I spelled load wrong. Okay. What is this error message? Alright, that should be good. It's still showing up as errors because we haven't returned a value yet. So let's create an asset map. It's gonna be what we return as our asset. Sorry for that, those typos, probably really annoying. Okay. I made another typo, okay. Over here we're gonna log that we did load our map. And let's just print out the path that we loaded. And this should be the, we're not gonna use this, let's just satisfy the Rust analyzer. That's all we need to do to load our map, load the data, but we have to actually spawn in our map now based on the data, and this is actually the part which you should pay attention to. Most of this was just boilerplate. Here, I'll just go over it again in case you need to copy it down. Or honestly, the source code, like if you just want to go to the source code here and copy in most of the boilerplate, you honestly could. Most of it doesn't need to be understood. This part you should probably understand though. Okay, so let's define a few structures that we need to load in our map into the actual game world. First thing we're gonna define is tiled layers storage. This is just gonna be a hash map with a list of a hash map that stores each layer as an entity. Corresponds to an index here. It's gonna be a component we're gonna put onto our tilemap entity. And then also create a tilemap handle. This is just gonna store our asset, which we just loaded in with the load function. And then this is a component that I decided to include by myself, but it's called tilemap load state. And we're gonna have a single boolean inside of it. Boolean. And basically how this works is if we set the loaded to false, then our loader will, what we're gonna write later is gonna despawn the current map and load in a new map. So basically when you want to switch levels, or when you don't even have a map spawned at all, loaded is false, so our loader will spawn in a map. If you want to change levels, you also set it to false, and then you change the handle to a new map, and the current map will be despawned by the function we're going to write, and a new map will be spawned in. Alright. And now finally let's define what components are going to make up our tilemap entity. So let's create a bundle. Call it tilemap bundle. We're gonna have obviously the tilemap handle as the first component. I spelled it wrong. We're gonna have tiled storage as another component. And then we're gonna have load state as, what should I call it? I'm just gonna call it load. Let's just call it loaded. Load state, whatever. Tiled map load state. And then, oh, I forgot to implement default for this. We're gonna have a transform component, global transform component. This is just so we don't have to keep, so we don't have to add in the transform component manually, and if we call the default, it'll just add it in by itself. And then I'm gonna add a tilemap render settings component. I just imported that. This is a Bevy ECS tilemap component. We're not gonna actually make use of it, but I'm pretty sure it needs to be added to the component before anything's rendered. Not sure though. And now we can write the actual function. First, let's register our loader though. We just wrote all that code for nothing then if we didn't register it. So let's .register asset loader, tiled loader. And the new function we're gonna write is gonna run every update. Process maps. Okay. Process maps. This is gonna be the function that actually spawns in all of our maps, or updates maps when we want to load new ones. First, let's make a commands parameter. To access the maps, we're gonna need to have this resource here. And then just add in some queries, which we're gonna use later. Oh my god. Import that. Map query, this is gonna be just how we access the main entity, which has all of our tilemap components inside of it. that should be all we need for now. Obviously, we're gonna need to add a lot of other types of loading later on, but let's first access our map query, whatever entities are in our map query. Map handle, load state, and then a layer storage variable and a render settings variable, which we're probably not going to use, I think, too much. Let me just new line this so you can see it. And then we're gonna only run this, we're gonna only do anything if our load state is not loaded. So if it is loaded, we're just gonna return and not do anything. If it is not loaded though, we're gonna go ahead and access our tile map data. Let's set the flag to loaded so that it doesn't load like multiple times. Loading every frame would be very bad for performance. And then I'm gonna actually spawn in stuff, so let's iterate over. Actually, we have to despawn all of the maps that are currently on the scene first, so let's iterate through all the layers first. Existing layers. And then access each tile inside of... Yeah, let's access the tiles after we access the layers. So for tile in layer tile storage dot iterate dot flatten, we're gonna despawn these tile entities, and after we despawn the tiles in each layer, we despawn the layers themselves. All right. What is this? Oh, gotta put it inside. Okay, after we've despawned all of the existing tiles, we can start creating new tiles. How this works is, since tiled lets you have multiple tile sets in a single layer, we have to iterate first over the tile sets, and then spawn the layers that have each tile set in it. You can't just iterate through the layers. I don't know if I explained that in the best way, but you'll see how this works after I finish writing these two for loops. So first iterate through the tile sets. Let's get the data for each tile set. So tilemap texture. Get the tile size based on the tile set. The reason we're doing this is so we don't have to manually tell our game that the tile width and the tile height is 16. It'll just grab the data from our file, from our tiled file, and it'll know. So we're gonna have to import this because it's another function. And spacing, I don't really use this much, but it's nice to have some extra features. Tilemap spacing. Grab the spacing. I think it's just spacing. Yeah, it is just spacing. Also have to import this. And And now we're ready to iterate through all the layers in our tile map. So for layer index, layer in tiled map.map.layers.enumerate. And now we only want to we're only dealing with what we call tile layers. Wait, let me just show you. So we have tile layers and then also object layers. I'm actually going to create the object layer right now. It's the player object layer. And let's spawn the player over here because why not? This is a tile layer, so you place tiles and whatever. That's what we're focusing on loading right now. And then we've got object layers as well. You can place objects with I. So that's what we're doing. I, and then just click. This is where we want to spawn our player. Object layers are useful because you can add like properties to the objects. If I wanted to, I could add a name, player. We're not going to go into parsing properties, but it's pretty easy, so you could probably just read up on the documentation on the internet for it. Anyway, right now we're just loading the tiled layers. Access the offset of the layer. I don't really use layer offsets, but they exist, so it's good to cover all your corners when loading stuff. And now we're gonna match the layer type. So what we want to do is load in a layer if it is a tiled layer. And we are gonna cover object layers later, but right now I'm just gonna make everything else not do anything. Actually, I'm just gonna log. What should I log? I'm gonna log unsupported layer and then the layer name. Okay. Now back to loading tile layers. We first remember before when I said to not check the infinite on the tile size, on the map size. Well, we're just gonna make sure that we don't load those infinite layer types. So we're gonna, if the layer has a finite layer type, we can grab the layer data. The map size, basically this thing, 30 by 20 tiles. That's what we're gonna get with the map size. So the X is obviously the width, Y is the height. And we have to import this because. And then the grid size, I'm gonna grab that information as well. I'm pretty sure we need to feed all of these into our component, so nothing will render if we don't get all the information. And X. It's nice that all of these different types of sizes are pretty much structured the same way. And we have to grab the map type. In this video, I'm only gonna... We're basically just using rectangular tiles, or what is called an orthogonal tile in the Bevy ECS tilemap world. But we can get the type nonetheless. My collision algorithm will only work for the orthogonal type, but the rendering is probably going to work differently, so might as well write more boilerplate. I'm just gonna copy this code to be quicker. This is orthogonal is what we want. That's what we're gonna be using. Tilemap type, gotta import that. What? Oh wait. I think we might have to fill out everything. I don't know if that's the error though. Gotta import that as well. These are both isometric coordinate systems. ISO chord system. This one is called, obviously. Oh, this is a diamond. And this is staggered. Alright. Now we can actually spawn in our tiles. So create a tile storage. And then make it the size of our map. And let's spawn in the layer entity as an empty entity with no components. And then we can iterate, create a nested for loop over the map sizes. Now, let me show you something. So if I put my mouse here, if you look down here, you should be able to see the coordinates. Why are the coordinates 0, 0, 320? Well, this is the tiled coordinate system, has its origin on the top left of the screen, but the Bevy coordinate system has it on the bottom left. So we need to transform from the tiled coordinate system to the Bevy coordinate system. And the x values are the same, but to go from the tiled coordinate system to the Bevy coordinate system, you have to subtract the tiled coordinate, so 320, from the height of the map, which is also 320. So if we're down here, it should be 0, 0, because 320 minus 320 is 0. So let's create mapped coordinates. Mapped y would be height of the map minus 1 minus y. Okay, and we're minusing 1 because it's based on index, but that's it. And then the x should it's just the x. I'm just putting it here to be cleaner with the code. Now we need to see if the tile actually exists at that point and it's not just empty. So create a match statement. Mapped x, mapped y. If there is a tile there, we're gonna return the tile, so t. If there's not, we're just gonna exit out of the loop, continue, and go to the next tile. And of course, since we're iterating, since our first loop goes through the tile set, if none of the tiles in the current layer have the tile set index, or at least if the tile in this layer doesn't have the tile set index that we're currently iterating over, we're also gonna have to continue to the next tile. It's a bit confusing the way this is structured, but that's what you have to do when tile allows multiple tile sets per layer. And then I'm gonna grab the tile data, another match statement. It's basically the same thing as grabbing the layer tile. And then We're gonna get the texture index of our current. These are all boilerplate that we have to write to actually spawn in our tile, but shouldn't be that hard. Just copy what I'm doing and you should be fine. The tile position, obviously we already have that information from our for loop. And now we can spawn in, oh, let's import tile position first. And now we can spawn in our tile entity. So first we need, oh, we can just use a bundle, tile bundle. Tile bundle is built into Bevy ECS tilemap. We don't have to do it ourselves. So our position is obviously tile pos. Tilemap ID is our texture index. Texture index. Oh, it's not. Wait. This should be our. We can set the ID to the layer entity. The ID of our layer entity. I went out of order there. Let's import this. Now we can find our texture index. Texture index. And the flip. Remember when I placed tiles X, Y. If I click X and Y or whatever, it flips. To make sure that functionality works, we have to initialize the tile flip component. I forgot to import it. Hold up. X flip is what is called flip H. Y flip is flip V. And I don't know what D flip is. I actually have zero idea. But the examples had it, so I'm just gonna put it there. And let's access the ID instead of the useless entity commands. And then we should be good to go on our tiles after we set the tile storage position to this entity. And then down here, we're gonna spawn, or we're gonna add all the components for our layer. Let's insert our tile map bundle. It's another built-in, it's another built-in bundle from Bevy ECS tilemap, which we need to import. Grid size, this is just all information we need to fill out. Map size. Storage is tile storage. Texture is tilemap texture. Then tile size, spacing. Anchor. I like to set the anchor to the bottom left because then if the tile map is at 0, where's my object? Okay, over here, then this coordinate will correspond to 0, 0, just like in Bevy space. I didn't know how to set the anchor before. I didn't realize that this was a thing, so I had to introduce a lot of offsets in my collision algorithm. But now, if you set it to bottom left, it's most compatible with Bevy and also makes collision algorithms a lot easier to implement. Just gonna finish filling out this information. This is again a lot of boilerplate. I think this is probably the hardest part of the video, even though it's just boilerplate. Let's set the layer storage. Let's insert this into the layer storage. So layer index, layer entity. Okay. We should be offset Y. Wait, what? How is that unused? Let's see. Oh my god, this should be Y. So yeah, we're almost basically done with loading in our tile maps. I'm just gonna leave it be like this for now until we figure out how to load in our object layers. But let's test out whether this actually works. Let's create a level folder, level.rs, mod.rs, and then include the level folder in this module. Okay, so tilemap plugin. Let's also include the tiled plugin here. In our level file, this is the file which we're going to use to set up our scene. So let's create another plugin called level plugin. Then we're going to create a startup function. Startup called setup. And then let's create a setup function. We're going to spawn in our map from this. We're going to load our map and then spawn it in this function. So we're going to have a commands to spawn and asset server to load in our file. First, let's make the map handle asset. Let's tiled map handle asset server dot load our map/map.tmx. And now we can spawn in our tiled map bundle. All we have to do is insert the handle, everything else should be automatically initialized. I don't know why I made this mutable. It does not need to be mutable. And then add systems. I messed up. Nothing. We can't see anything if we don't add a camera, so let's spawn in a camera real quick. Camera 2D. This is gonna be changed later, but for now let's just see if our game works. So insert the level plugin in our game plugin and run our code, and let's see. Oh, first try, it works first try. Obviously our camera is pretty zoomed out. This is a 1:1 scale at the moment, so yeah. What is our next step? After we've already loaded our map, now let's create a player. I think the best way to start doing this is to first create a object layer loading resource. System. So we know where to spawn the player in from the tiled map. So let's start doing that. Okay, so let's define a new resource. Object layers. So I'm gonna create two hash maps here. The first hash map is going to be a hash map of all the object data in a layer. This is also tiled type. If I go into the definition, it contains all the information of an object. We're really only going to be using the position of it in this video. Okay, and then we're also going to have loader systems. So since we don't know what to do with the data, we're gonna have a hash map of system IDs, which are just a way of defining systems just like this one. So each time we're trying to load in the layer, we're gonna run a system, and the system is gonna access the layer data and decide what to do with the objects. Okay, so now let's go down here and where we're matching the layer data types, let's add a new type. We're gonna handle object layers now. Now this is actually a lot easier than tiled layers for now, because all we have to really do is pass in object data to the resource and have everything else just work. Object layer. Okay. Let's first access let's init this resource first. Yeah, I also want to create another resource called level data. Let me think. This is so we can access information such as the height of the map or the width of the map inside of our actual game. We're gonna have to use this later on for constraining the camera to our tile map. So let's create an option map and a collision map. Collision map is gonna be for later. Later we're gonna use this collision map to detect collisions. It's gonna be a 1D array, but we can use flatten functions. 1D arrays are a lot more efficient than 2D ones. Let's init both of these resources. Level data. And other resource we're initting, what is it called? Object layers. This is fine because it'll just create 2 empty hash maps, which is what we want anyway. Now to load in the object layers, we should just be able to first get the list of objects, which is do by going object layer.object data. Then we're going to turn this into a vector instead of a slice, because you can't store slices in structs very easily. And we're going to call this vect object data. And then we can insert this into the hash map. Oh, I didn't access this resource yet. Let's actually access both resources over here. Res mutable, object layers, and level data. We're also going to make that mutable. Res mute level data. So we're inserting, should be the layer name, layer.name.clone and data. And now we just want to call the system. So object layers dot loader systems. And now we run that system with commands. System. Just to note, the loader systems, we're gonna initialize those at startup. So we're not creating them in here. We're creating them in our actual code. Okay, what are these warnings? Unused input. Okay, I don't think you need that. Another warning. Yeah, we're gonna do this. This is not a warning that we should really care about. We'll deal with the level data later. For now, let's just spawn in the. Actually, let's do the level data right now. I wanna create a constrained camera function first. So over here, we can pass in our map variable. to our resource, and then we have to find a way to implement or find a way to init the collision map. And I think we can do that. Where can we do this? Okay, so inside here, if our layer name is collision, we can init a collision map. Of size. Okay, so this is the total number of tiles that should be in a rectangular map. And then to actually, this is a bit inefficient actually. I'm gonna check if the layer name is collision again every single time. It's a space here. Now we're gonna set the collision map. Mapped x plus mapped y times map size.x as I32 as usize. We set that to 1, so 1 means that it is a solid position. This works again because over here we reset all the values to 0 and then these set them to 1. Let's just test to see if our collision map is correct by printing it out. I'm gonna check if layer.name equals collision again over here. We're gonna delete this later, but I just want to see if our code works. Print. Okay, now we're gonna iterate over level data dot collision map dot length, and then if I modulus, I'm just gonna actually, we already have the map size here. Okay, this should print our map out. What is this? Oh. Why is there a panic? 192. Oh, we don't have any systems. I'm just gonna comment this out for now. And does that look right? One. I don't know what these are, but looks mostly right to me. Maybe I have some invisible tiles here. Check this. I mean, it looks correct enough. Okay. I'm just gonna hope that it's right. Comment this out because we don't need to print it out every time. Okay. Now it's did we uncomment it already? I already forgot. Okay. Now onto the player class. Let's create a folder called player file, and include the player folder over here. Let's create plugin called player plugin. At startup, let's insert a function that will just load our player. And what should I call this function? Add loader, because we're going to be inserting our player loading function to our tiled object layer resource. So obviously we gotta access our object layers resource. Res mute object layers. And we also need a commands to register our system. Just create another function for now. Load player. The system is not going to do anything yet. We will write it later. So our object layer is called players. So you can do text in here. I did not even know. Player, and then register the system to get the system ID. Load player, and this needs to be a string. To load our player, right now I'm just gonna spawn the player as a sprite, like the first frame of the sprite, just to see if our object loading is working. Asset server, texture atlas layouts. First, let's get the object data. Since we're expecting that there's only one player in our layer, we can just grab the first object in the array, which I'm gonna do right after I grab the whole object data. I have to access. So object layers dot layer data, that gives us the vector. We can get the specific object by just taking the first element from that vector. And I'm gonna grab a reference to it since I don't think we're gonna be modifying it or anything. And we can grab the tiled map data as well, so that, because we need the dimensions of the map to convert coordinate systems, we need to access level data as well. Okay. Does not need to be mutable. We just reorganize this. I'm gonna define the player size as vector 2. Now, how did I get these values? I actually have. Let me open the player file. So the height is 38, and the x height, the x width, measured that out to be 12. Whatever. Guess it was 12 instead of 13. Okay. And then we're gonna convert. Oh, we have to create some helpers first. Create a new file called helpers. Okay. And then inside of helpers, we're going to create a function to convert between coordinate systems. So create a function to convert from the tiled to the world position. So from tiled to world position. Tiled position passed in as a vector 2. And then since we have easy access to the map, how about we just pass in that as well. And then x value remains the same. The y value is the tiled map's height times the tiled map's tile height. It's f32 minus the x position that was originally given to us. And we have to return a vector 2. Right. Now, back in our player function, we can finally get the position of the player. So, tiled to world position. The position is just object.x as f32, object.y as f32. And we have our map, which we can just pass into the function. Oh. The number of frames I saw, let me just go over this first. Got 3 animations. And what it looks like, this is the sprite sheet that I have. Basically, we need to split each frame like this. So each frame for me is 24 by 38. And we do this using the texture atlas feature in Bevy. So let's define the frame count. Oh yeah, to export in ASprite, you can go File, Export, Export Spritesheet, and make sure you're by rows because that's the way we're going to be sectioning our Spritesheet. Anyway, there's 19 total frames in my animation, so. And then the frame size I just went over is uvec2, which is just the usize version of, or I think it's u32. Yeah, u32 version of the vector 2. I'm not going to be doing any animations yet, but for now, let's just make the player freeze on the first frame. Let's create a texture atlas layout. And we can spawn in our player right now, but he is not going to be able to do anything until we write more code. So we're gonna make his transform position extend and put it on the 10 on Z layer. Create a sprite. The image we're just gonna load in right now. This is not very optimized. We're supposed to load in everything before we actually spawn in any objects, but this is a beginner tutorial, so don't have to go that in depth. Texture atlas. Index is 0, so this will put us on the first frame. And everything should be at default. This should place our player over there. This does not need to be mutable. What else do I have? Unused. I think we should be fine. For now at least. Put the player plugin in, or game plugin. And player should spawn in once we run the code. What is going on? Oh, it already ran. It was running the whole time? Okay. Let's run again. Yeah, you can see our player up there. He's kind of tiny right now since we haven't written any code to help out with. Okay. So now I'd like to I'd like to write some camera code first since it's very uncomfortable looking at the player from so far away. So let's create a camera folder. Camera file. And link the camera file, this module file. Okay, so first let's just remove this code because we don't want to spawn two cameras. Create a plugin, camera plugin. Then we're gonna add a new system that spawns a camera at startup. All we need is a commands variable. And let's spawn a camera so that each native pixel is 4 by 4 pixels. I think that should give a good view. Spawn it at the 0, 0 for now. And then create a projection, which is how we're going to control how zoomed in the camera is. Pixel ratio is a variable we're going to create later. And then I just want to make sure we're able to see everything. So near plane 1000, far plane negative 1000. Default 2D, and this should spawn in a camera with good scale once I establish this variable. And if we add in our camera plugin, oh, there's a Bevy camera plugin too. I should name this differently. Whatever. So yeah, let's run this and see how zoomed in our camera is. Oh, everything's blurry right now, and that's because we did not set the image plugin to nearest. So go to our main file and then set default plugins. So set the image plugin to default nearest, and this should give us a good. This is what I usually do for pixel art because resolutions are really small. This is a better size. Now, if you see the tile map, our camera is not really constrained to the tile map, so we can't really see anything. So let's create a function for that. First, create a component that identifies our main camera. Camera controller is what I'm gonna call it. And we can spawn camera controller over here. Alright. Let's create an update camera function. It's gonna constrain our camera and make it follow the player actually for now. Let's also create a player component so that we can identify the player. player should have. Let's not initialize any variables for the player yet. I'll just write the camera. Update camera function first. Let's just add in a player structure for now. Gonna query for our camera, and since we're also querying for our player, we have to make sure the queries are disjoint, so we make 2 queries with and without function in both of them. Import the player, and then in the player query we're gonna make sure that there's no camera controller query. No camera controller component. And we're gonna need the level data so that we can make sure that the camera stays within bounds of the level. This gives us the width and height of our level, so we're gonna need that information. Let's access the query for our camera first. And access the player query as well. And then inside of that, we're gonna set the transform of our camera to the player transform as well. And this is gonna make sure our camera follows our player. Obviously our player doesn't really do anything right now, so it's just gonna stay in one place, but later on it's also gonna follow the player. And now let's access the map variable inside of our level data to get the width and height of our map. And access the size of the window basically with our camera viewport. I don't know why for some reason it doesn't zoom in for the size doesn't change even though our orthographic projection is changing. So you're gonna have to deal with that in a bit. So the map width should be the map's tile width times the map's actual width, and we're going to make that a float variable, and the height is the same process. And then we're going to get the half size of our window so that we can perform some calculations to make sure that we never see what's outside of the tile map. So that's the size, and the size on the X and Y over 2 times the pixel ratio, which we'll import from, wait, what is going on here? Oh, vec2, alright. And now we can do some checks and constrain the camera accordingly. I made another typo, so we're gonna correct that. So this is basically saying if the left side of the camera leaves 0, which is the edge of the screen, since we defined bottom left as the anchor point, then we'll just reset the camera position to what would make it so that it's not outside of the screen. And we have to repeat this for each of the bounds of the level. So also, if the right side of the screen is greater than the total width of the map, so map width, we're gonna have to transform the X value to the width of the map minus the half size of our screen. And then we can do the same thing for the top of the screen. So if the top of the screen is greater than the height of the map, we can transform our Y position to be the height of the map minus the half size of the screen. And now our final thing is to check if the bottom of the screen is less than 0, because that's the bottom of the map. Then we can change the Y position to be half. So this is basically making sure that it never goes, the bottom of our screen never goes past 0. So that should be all for camera functions. We're almost done. All we have to do is write the physics for our player and controls for our player. So let's make sure that the function is run every frame. Update camera. Actually, I'm gonna run this in the post up. Wait, that doesn't do anything. Never mind. Okay, so looks right to me. It should be more apparent if I move him down here. If you move him down here, it should just clamp to the bottom left of the screen. Yeah. Okay, so done with cameras. Next thing I want to do is implement a collision algorithm for the player in the tile map. But before that, we have to do some create a helper class, AABB. That's called aligned axis bounding box, if I remember clearly. So let's do that real quick. Oh yeah, just to, if anyone knows what X and A is, they have a list of samples. I sort of adapted this method from the X and A platformer example. So if anyone knows what that is, that's the method I adapted this collision algorithm from. Anyways, let's link the AABB axis aligned bounding box class. And all we really need to do is write this one function. Actually, you have to write a lot of functions. I scratch that, because we're kind of just writing an entire helper class. Default phone access aligned bounding box. The center of the box we define as a vector 2, and the half size of the box we're also going to define as a vector 2. Now let's implement all the functions we need. First, we need a constructor. Obviously, it's pretty easy. You just do this, and you just put in the variables. That's it. Then there's some helper functions I'm just gonna write. They don't need it to be mutable actually. The right of the box, that's the center of the box plus the half size of the box. What? Oh, self.center. I'm slow. And then the left of the box follows the same principle. Center.x minus half size.x. The top of the box, that's also really simple. We use y values this time. The bottom of the box, oh god, you don't need a semicolon. And now let's write the actual important functions for our collision algorithm. It's something called get intersection depth. With another axis bounding box. Let me just pull up paint. If there's two boxes and then they're colliding like this, what we basically want is how far in is this box pushed on the x axis and how much is it pushed in on the y axis. And so if it's on this side, okay, I think it'll be clearer once I actually write the code, but that's basically the idea of what we're doing. Okay, you can use this for what we're basically going to be doing in our collision algorithm. Is we have a list of tiles. Let's say these are tiles, and let's say these are the tiles which are solid, and our player, let's say this is actually, let's make this better. Let's make this also solid. Let's say our player is this yellow box. I'm just gonna make it black and then shade it yellow. Well, basically we find out which tiles our player is capable of being in. So that would be this one, this one, this one, and this one. And for each tile, if it's solid, we find out whether the intersection depth, we find the intersection depth, and we just push our player out of the tile. That's basically what's going on in our collision algorithm. That's why we're implementing this function right now. That explanation was a little whack, but I guess it works. Also, I don't really have my drawing tablet on hand right now, so have to bear with this mess. Alright, so the first thing we do is find the minimum why did I make it mutable? You find the minimum distance, which is basically how far the boxes can be from each other on the X and Y axis so that they don't collide. And this is literally just the half sizes added together. It's pretty simple. Think about it like, okay, let me pull up Paint again. There's a box here and a box here. Here. You see how we define their centers as this and this. The minimum distance they can be from each other without touching is the half size over here added by the half size over here. That's basically it, yeah. And then we find the actual distance, which we'll use to check whether it's smaller or bigger. So if let's put the depth variable as 0 first, because we can just return this if they're not colliding at all. So if the absolute value of the x value is greater than the minimum distance of the x value, or the absolute value of the y distance is greater than or equal to the minimum distance on the y, that means they're not colliding. Because if I do this again, that means they're farther apart than this, and that means they're not colliding at all. So we're just going to return the depth, which is 0 right now. Oh, I didn't put a return for this. Okay. And then now we check. Now that we've eliminated the cases where they are not intersecting, that means that after this point they are intersecting. So we need to determine how much they're intersecting by, which is actually really easy, but we also need to know the sign of what they're intersecting by. So if the x distance is greater than 0, that means that the self box is on the right and should intersect negatively. So basically our depth on the x would be minimum distance dot x minus distance dot x, and this should be negative because minimum distance dot x is always positive. And if this is if distance dot x is greater than, or actually wait, let me think about this. Yeah, okay, so this would mean that okay, so I figured it out. If the x distance is greater than 0, that means when we subtracted the center of our box from the box we're comparing to. Our box should be on the right since it's larger than 0. And that means that the depth should intersect negatively because here if we go like this is a negative intersection from our box to this box. Yeah, that's basically the principle of what we're doing here. And then otherwise self is on the left and should intersect positively. So x would be negative distance dot x minus minimum distance dot x. And then we do the same for the y axis. This means that self is on top, and if self is on top, we should intersect negatively. Otherwise, self is on the bottom, and if self is on the bottom, then y should, where did my, okay, should intersect positively. And then finally we just return the depth, and done with our axis aligned bounding box collisions. All we need to do is use this function now in our player class. So we're gonna create an update physics function. Or actually no, let's call it handle collisions. And the special thing about this is we're going to be running it not in an update loop, but in what is a fixed update loop. So what is a fixed update loop? Well, basically, regardless of your frame rate, the fixed update will run a fixed amount of times. So that's why most physics is handled on a fixed update instead of a normal frame-based update. So yeah, I'm not gonna go like our fixed update. It might seem a bit choppy because obviously it's not running every frame. There are ways to interpolate so that it's quicker, but I'm not gonna go interpolate so that it runs smoother. But I'm not gonna go over that in this video. There's an article online, I believe it's called Fix Your Time Step. That goes into pretty good detail about the interpolation, so read that article. Okay, let's go back to the handle collisions function. And we're gonna first access level data because that's where our collision map is stored, and also make a query which just accesses our player. There's only one player in the world. I don't really want to add more than one player, so I'm just gonna single mute the query instead of just making a for loop over the query. And then let's access our map. We're gonna need to access the height and width of our map later on to transform between coordinate systems, but what the? And then let's construct an axis line bounding box for our player. This is pretty easy. We know the position of our player is just XY. It's a pretty good helper function. And then the half size. You know what? Let's define some variables for our player. Speed. We're gonna make him jump later, so jump force. And then we've got the velocity, half size, which is what we're about to use, whether he's on the ground or not. Horizontal, this is gonna be part of our input, so input var, I don't know, I'm just gonna put that there. And then whether he I'm just gonna write everything in right now so that we don't have to keep switching between the two views. We're gonna be using all these variables later. Anyways, let's also define some constants. Gravity. Okay. Terminal velocity. Jump time. These might not all make sense right now, but I just wanted to not switch between screens and like make everything really hard to follow. Okay. Oh wait, what did I do there? 1.4. Now we can access the half size. Obviously, we have to initialize all these variables now. These are all from our constants, most of them at least. Jump timer is going to start at 0. Jump force is just jump force. Speed. Really? I thought I identified this as an integer. I'm gonna use an integer for this. Okay, that should be all of our variables defined. So in handle collisions, get the player bounding box. Also store the tile size because that's gonna be really important. Okay, so basically what we're gonna be doing, let me pull this up again, is, let's say this is a grid of tiles. And our player is about this size. We're gonna be, so what tiles do we need to iterate over? Oh, this one, this one, this one, this one, this one, and this one. How do we do that? Well, we get the, should I color code? No. Let's get we get the right position of our player and the left position of our player, and we find out which tiles these fall between. So our left position would fall between this row of or this column of tiles, and our right would fall between this column of tiles. We're gonna basically, and then we do the same thing for our top and our bottom, this row of tiles and this row of tiles. So then we do like a nested for loop, iterating through all of these tiles and seeing which intersect with our player. So if this were a solid tile, we would detect it and move our player out of it. That's basically the idea of the algorithm. So let's find our left tile. So how you can do that is just dividing by the tile size, finding the floor value, and finally converting it to a usize variable, which will let us access the index. For the right tile, it's the same idea, except this time we use the ceiling variable, and then we use not the left but the right position. We also divide by tile size. It's a little different for the y variables. So the top tile, because our map is stored. So let's say we basically have to subtract the y position from the height, because the index of our array is stored differently. So let me just pull up Notepad. If you go, so let's say this is our array. If we're at 0, 0, we want to access this, but if you go 0, 0 in this array, it'll just go here. So basically you have to flip the y value. Alright, that should be clear, I think. Alright. So we got the top. Then you divide by tile size. Make it a U size, yeah, okay. And the bottom tile, same principle again. This is not ceiling anymore, this is floor. And instead we use the bottom. Now we're ready to write our nested for loop. First I'm gonna reset whether the player is grounded or not. For X in so the tile bounds, this is the bounding box of the tile we're currently on. We can find that. First, the center would be X as F32. This is pretty self-explanatory. And the Y value is a little bit different. We have to flip it again. And since we're finding the center of the tile, and so we basically need to go like, right now we have this position, but we need the center of the tile, so we need to go here. We gotta add the half size of our tile. So back to splat is just a fancy way of putting one value in both the X and Y axis. So if I do this, we should be good. What went? Oh, I forgot to supply the size of the tile, which we can, the half size of the tile, which is again just the tile size over 2. Okay. What went wrong now? Mismatch closing delimit. What? Yo, this looks really messy. Hold up. Let me just reorder this. Okay. I'm gonna reformat this file. Okay, now copy that down. That looks a lot better. Let's find the depth now with our helper function. Get intersection depth with our tile bounds. And then the absolute depth would just be depth times depth.abs. If this depth is not 0, so basically if we're intersecting, we check whether the tile is solid at our location. So it's a 1D array, so we're gonna have to do some operations like, I'm gonna let you wrap your own head around this. I think this should be pretty easy to understand. If you look at this, if we want to go to, for example, actually I'm just gonna explain it. If we go to 2, if we want to go to 2, 2, which is at this position, obviously the X is 2, right? And then each row consists of 1, 2, 3, 5 tiles. 5 times 2, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That gives you 2, 2. Okay. So There's actually two ways to resolve the collision if you go back to the paint. You can either go up, or if this tile is red, you can either go up the Y depth and you would be out of the tile, or you could go to the left and you would also be out of the tile. But obviously this is like, you should be going up here because it's a lot less to go up than to go right. I mean to the left. So basically we take the path of least resistance, I guess, like in electromagnetism. So we want to go up because that's less distance. So we can do a check here. If absolute depth.y is less than absolute depth.x, then that means we're gonna go y. We're gonna go the y direction. So add the depth of y to the transform. Okay, another thing here is if we're going up, right? If we're where's my paint? If we're moving up, that means we hit a ground tile. That means our player is basically on the ground. So I'm gonna check if depth is greater than 0 to see if it's moving up. And if it is, I'm gonna set the player's grounded to true. Otherwise, we're gonna move him on the X, and all we have to do over here is add X. Finally, after we've made all these changes, we have to update the bounding box of the player, make sure that he's not being moved around in other tiles, or if he's colliding with another tile after being moved on. I don't know, this is kind of strange, but we have to update him again, I guess. Okay. And this is all we need to handle collisions. Let's create another function called update physics. And this is basically gonna update the position of the player based on his velocity. It's also gonna update other timers. Actually, this function, I'm gonna update his input first. Input. And then we're gonna query for the player. So if we press the left arrow, key code arrow left, we're gonna set this horizontal. We're gonna subtract 1 from it, and if we press the right arrow, I'm gonna add 1 to it. So at the end of these two operations, we know which direction our player is going to be moving in. And then I'm going to do the same for, actually not do the same, but if we want to jump, I'm going to set it to Z. I'm just used to, yeah, Z is kind of a strange choice for some people, but I like these inputs. We're going to set the jump timer to the jump time. And if we release this, I'm going to set the jump timer to 0. So later on, we're actually going to implement the physics for this. If the jump timer is greater than 0, we're going to be applying a jump force, and gravity is not going to apply to the player. But right now, I just want these variables to be initialized. And then we're gonna update the physics of the player because all of this is useless if we just have the input. And then let's update our players. All we need is the transform of our player and player velocity, so that's basically what we're going to be accessing with this query. So the velocity of the player we're going to set to player.horizontal as the float variable times the speed of the player. That's pretty, I think that should be very easy to understand. And then we check if the jump timer is greater than 0, and if it is, we're gonna make a jump force, which is just the player. But why am I need to initialize this as a local variable? Then add the jump force to the y velocity of the player. Otherwise, we're gonna apply gravity to the player. Player.velocity.y minus equals gravity. And then if our velocity has exceeded the terminal velocity, so that's what this is doing a check for, we're gonna set the velocity of the player, the y velocity. I don't think we need one for the x because we're not really using any acceleration there. We'll set it to terminal velocity times the signum, which is just the sign component of a float variable. We're just capping it basically. And then we're gonna apply the actual velocities. If the player is grounded, I'm gonna make sure that their velocity is 0. I don't want the player to just clip through the ground with infinite velocity. And it's important that this is after this check, or wait, this is after this check, because I want the player to at least be a little clipped into the ground each time, because that's how our check makes sure they're grounded. If you were not clipped through the ground each time, it would be very consistent on telling if he's grounded or not, and that's not what we want. So yeah. And then okay, so this should make it so that we can move the player around. Obviously we don't have animations next, which is the next step, but let's just make sure this works for now. Add updates for handle input. You can't handle input in the fixed update, which is why I even have this function in the first place. And then in the fixed update, we want handle collisions, and then also let's add our other function, update physics, and let's make sure it runs before handle collisions so that we can make sure the ground check is done. Okay, let's test this out. If it doesn't work, that would be very, very sad. It seems to be working for now. You can jump, hold longer to jump more. Pretty much all we have left to do is animations, because this guy is not look very mobile right now when he's moving. Okay, I'm gonna create an animation class or animation structure for this Rust. Usually I would just have you copy this in. Should be pretty easy to understand. I'm just gonna try to speedrun this. The video is already getting really long. So did I link it? Yeah, I did link it. Okay. First, just use Bevy prelude times. I'm gonna call this the Atlas animation plugin. And then we're gonna be adding systems here. I'm gonna do it post update since we want all our logic to run before we actually update any of the animations. Update animations. Okay. Let's derive some components first. Animator, this is what it's going to be used to actually animate our players. Animation, current animation, previous animation. This is to decide whether we want to switch animations or not, or switch frames when you run a new animation. Then we're going to have a hash map of animations. And then a timer, which basically indicates whether we need to switch frames or not. Oh, why did I import that? Okay, wait, I'm supposed to create my own. Frame duration, how long each frame will stay on screen. The start actually starts at if one is basically the first frame. That's what I'm gonna be using, because if I go into my animation program, 1 to 8, I don't want to say 0 to 7. That's kind of confusing. I want to make sure everything's universal. So yeah, and then the final is this animation going to loop or not. Okay, now we just have to write this update animations function, add some animations to our player, and we're basically done. Why am I writing it in here? Okay. If you couldn't tell, I don't usually do live tutorials, so I might not be very good at narrating. And a query for all animator query should be the name. So we're gonna query for every sprite with an animator in it. And then for each of these, we're gonna subtract seconds from the timer. And then we're gonna access the atlas of the sprite. This is how we change the index of our animation. So also, if the current animation is not the same as the animation of the previous frame, this means that we have a new animation. So we should switch our current frame first. Let's access the animation though. So atlas.index is equal to animation.start -1. The reason we do -1 is because this thing, it doesn't use the same indexing system as like ASprite, for example. So I want to set it to 1 in ASprite. It would be 0 for the atlas. So that's why -1. And then the timer, obviously we have to reset that. Okay. And now, what to do if we want to go to the next frame. First, get the animation. Actually, I'm just going to copy this. And then the timer, we're resetting it just like we did if we found a new animation. And then the index, we're adding 1 to that. Oh, we have to, what did I, okay. If the index is greater than the end of the animation, then we reset it to the start of the animation if it's looping. Otherwise, we just stop the animation. So basically we just set the index to the end of the animation. Okay, so this should be our animation plugin. Let's just add this to our game real quick. And now we have to actually add animations for our player. So in our load player function, we got to change a lot of stuff. let's create an animation hash map. And then insert an animation. I'm just gonna, so 1 to 8, 9 to 14, and 15 to 19. This jump animation is pretty kind of quirky, I don't know. Right. Insert idle. I'll make this lowercase just for compatibility. Oh, we didn't import hash map either. So this should start at 1 and at 8. Frame duration 0.1, looping. Idle should loop, so idle is true. Import this. I should name these differently. Probably name it like Atlas animation or something. Second animation will go from 9 to 14. And it's also looping. And then, what is this called again? Run. And jump. So, my jump animation, I actually just added this frame. This frame shouldn't actually be in the animation. It's just here to... I'm just gonna go 16 to 19. So don't get confused because I skipped a frame. Now we need to add an animator component to our player. Animator, the initial animation, we're gonna make it idle. Animations, animations, and then everything else is just default. Obviously we have to import animator. Okay, now we have to create a function to update the animations, and we should be pretty much good. Update player animations. Obviously we have to query for the player. Player, sprites, and animator. So since there's only one player, obviously we're gonna only go single mute. If the player horizontal axis is greater than 0, so that means that the player is facing right, I'm gonna make the sprite not be flipped. If the player's horizontal axis is less than 0, that means he's facing to the left. I'm gonna make him flipped. If the player is not grounded, that means he's in the air. I'm gonna make him do the jump animation. And then if the player's player is standing still, or no, if the player, this means the player is somehow moving, we're gonna make him do a run animation. And finally, last priority, if nothing else, he's gonna be standing still, so we're gonna make him do an idle animation. And then let's place the system somewhere. I'll do it after the input. I think that's the after update player input. Let's make sure everything works the right way. We are basically done if this works. Something is wrong. So, let's see. It should be right. Did I make a mistake in my animation class? Oh, I see. So over here, we forgot to set the previous animation. That's actually my fault. Hope nobody messes up because of this. I hope everything else is right. Yeah, everything works fine. So yeah, that's my tutorial on how to make a 2D platformer with Bevy. If you guys want to see more of this content, like and subscribe. Yeah, see you guys in the next video.